All right, so back here with part 2 of the notes on 2.7, notes on limits at infinity. So in the previous video, we reviewed the end behavior, the limit as x approaches infinity, or the limit as x approaches negative infinity for polynomial functions. And so we're going to then take that and look at rational functions. Okay, so as long as you can recall the end behavior for polynomial functions, we're going to use that information to help us with the end behavior of rational functions. Remember, rational functions are when you have one polynomial function or any function really divided by a second function. Okay. All right, and so the first example we have is the limit as x approaches infinity of 3x to the fourth minus 7x plus 9 divided by 7x to the fourth minus 4. And last week when you watched the video on properties of limits, you should have discovered that you can take the limit as x approaches infinity for the top function and separately apply the limit as x approaches infinity for the bottom function and look at these as two separate limits. And then we can make a decision overall as to what the limit as x approaches infinity would be for the rational function. Okay, so let's look at the top. The limit as x approaches infinity of 3x to the fourth minus 7x plus 9. So this is a polynomial function if we're looking just at this top function here. Okay, and it has a positive leading coefficient. It has an even degree, which means that's going to look something like the very first graph that we made, positive leading coefficient, even degree. Both end behaviors are going to point in the upward direction. So as x approaches infinity, my right-sided behavior, my overall function will approach positive infinity. Similarly, the limit as x approaches infinity of 7x to the fourth minus 4, again, I should have parentheses around these two functions because the limit is being applied to both functions, okay? And 7x to the fourth minus 4 is a polynomial function. It has an even degree, so the end behaviors are going to move in the same direction. It has a positive leading coefficient, and so as I look at the right side of my graph, as x approaches infinity, the overall function is going to also approach positive infinity. Well, infinity divided by infinity is an indeterminate answer. We talked about this when we evaluated limits analytically. So I can't have infinity divided by infinity, which means that I need to take a look at another option. So one way that we're used to looking at these limits now is to look at the limits graphically. So I went ahead and in my calculator, I graphed the function 3x to the fourth minus 7x plus 9, all divided by 7x to the fourth minus 4. And you'll notice as you trace along this graph that as x approaches positive infinity, that's the right end behavior. As I look at the right side of that screen, it looks like I'm approaching a horizontal asymptote, okay? It looks like I'm approaching some horizontal line or some particular y value. And so, you know, when we end up analytically with infinity divided by infinity, yeah, I look at the graph and I see that I should actually approach a specific number as my right end behavior. There has to be another way to manipulate the function to get this y value. It looks like it's going to be, you know, y equals, I don't know, 0.2, 0.3, something like that will be my end behavior, what the y values are doing as x approaches infinity. Okay, so let's talk about what that would be, that manipulation. And so we're going to take a look at the end behavior model. That's what I'm going to call it, the end behavior model. And what the end behavior model does is it says, hey, when I look at the function, the strongest part of this function or the part that affects the growth of this function the most, is going to be the term with the highest degree. So in the numerator, the term with the highest degree is 3x to the fourth. So I'm going to look at the limit as x approaches infinity of 3x to the fourth in the numerator. And in the denominator, the term that has the biggest exponent is 7x to the fourth. Okay? For the remaining part of those functions, they really have to do with the y-intercept, that's the constant for each function, how the middle of the graph is affected. But in terms of the end behavior, how the graph is going to act as x goes to the right, as x approaches infinity, or as x approaches negative infinity, it's the leading terms, the terms with the largest degree, that are going to drive that end behavior. And so I'm going to look at the end behavior model, and I'm going to apply the limit to just the end behavior model. And what I notice is that my degrees are the same. Okay, and what I mean by the degrees are the same is that I have an x to the fourth term in the numerator, an x to the fourth term in the denominator, which means really the function in the top and the bottom are growing at relatively the same rate. Yeah, one has a 3 and one has a 7, but when I start substituting x values in, those x values are all going to be raised to the fourth power. And then the 3 and 7 will have a slight effect on that. If we were to simplify this expression algebraically, we would divide out those common terms, those x to the fourth divided by x to the fourth. Those are the same, and so x to the fourth divided by itself is 1. And so now really I'm applying the limit as x approaches infinity of 3 over 7. And as we said at the top, when you're applying a limit to a constant function, then as x approaches infinity or as x moves to the right, my y value is always the same. It's always going to be that constant of 3/7. And so moral of the story is, when you look at your end behavior model and the degrees are the same, take a look. Your final answer, which is, by the way, horizontal asymptote, we'll get that down in a second, your final answer is going to match the leading coefficients of your rational function. Okay, and so to finish this, we would say that the limit as x approaches infinity of 3/7 is 3/7. What that means is that there is a horizontal asymptote, which we saw when I graphed it for you. And the equation for that is y equals 3/7. So in one of the activities that you're going to do for Delta Math eventually is you're going to have to identify horizontal asymptotes. And horizontal asymptotes occur when the end behavior is approaching infinity or negative infinity for the x values. What are the y values approaching? Okay? So as x approaches infinity or negative infinity, if I'm approaching a constant y value, that's a horizontal asymptote. And I write that as y equals. Let's apply the same idea here in problem 6. So in problem 6, again, I could split this up into the limit as x approaches infinity for the numerator, the limit as x approaches infinity for the denominator. And again, I have a cubic function. So as x approaches infinity for this cubic function with positive exponent, I get infinity in the numerator. And as x approaches infinity in the denominator for that even degreed function with a positive leading coefficient, I again get infinity. Okay. But if I were to graph this, you would see, based on my new graph, which just looks like a slight variation of the previous graph, you would see, though, that that horizontal asymptote has shifted down a little bit. It looks like as x approaches infinity, I'm hovering around the x-axis, or a horizontal asymptote of y equals 0. So let's see if we come up with that algebraically, okay? So again, I'm going to take a look at our end behavior model, because the end behavior is driven by the leading term. The leading term is the term that has the biggest exponent. And so again, the limit as x approaches infinity. In the numerator, the term that has the biggest degree is 3x cubed. In the denominator, the term that has the biggest degree is 7x to the 4th. And now I'm going to apply the limit here. Okay, well, we can do something similar as we did in 5. We could say, well, I could simplify this expression, right? I have x cubed divided by x to the 4th. And when you divide like bases, you subtract exponents. So then I end up with the limit as x approaches infinity of 3 divided by 7x, right? X to the 1st. So let's think about this. The limit as x approaches infinity. And what that means is, I can't substitute infinity in for x. But what's going to happen is x is going to grow larger and larger as you start to input 100 and 1,000 and 10,000 and 100,000 and 1,000,000. Then my numbers overall in the denominator are going to get really large. And if I take 3 and I divide by 700,000, or 3 divided by 700 million, okay, I'm going to be getting close to 0. This is going to be equal to 0. And so notice in this particular case that the degree in the bottom, or the denominator, to use math terms, is larger. And so because the degree in the denominator is larger, when I substitute in larger and larger values for x, the bottom is going to grow much faster than the numerator, which means my overall number is going to approach 0. I do have a horizontal asymptote then, okay, at y equals 0. So again, anytime I get this numerical output, that would result in a horizontal asymptote. And we saw that when I graphed it for you, that as x approaches infinity, or as x moves to the right, my y values are approaching 0. All right, we're going to do one more part to this. So I will catch you on the other side.